So let's go back to, I was looking at the regularity of the weak product. So let's go back a moment there. So weak products, weak polynomials. So. The Gaussian free field. and I was discussing the regularity, okay? And essentially what we showed is that, okay, I took approximations and somehow, okay, you define somehow the weak product as a random field. So this will be in some point, this will be some limit in probability in LP, and if you do it fast enough, it's also almost sure. This depends on technical details, so let's skip for the moment. So the idea is that you construct, you regularize the Gaussian free field, then you take these Hermite polynomials. So this is a notation for these Hermite polynomials. Okay, I wrote you 2 or 3 of them, and then you take the limit. You need the limit to create a local object, and this is somehow some local functional, local function of the Gaussian free field. Okay, in the sense that we didn't prove it, but with this regularization I was using is slightly maybe uncomfortable to do it. But think about you regularize with a compactly supported test function, which convert to the delta function. Then somehow the support of this will be arbitrarily small in the limit, so this will be local, okay? So intuitively this works. I'm not using this property. I think all these questions of locality are not really in the notes in a very precise manner because we have more a serious issue, but somehow you have to keep this as a motivation because the reason we are doing all this effort, we want to take this limit because at the end we want local objects which for which we can hope to preserve this Markov property, okay? So I will stop to talk about this, ask question if you want, but somehow now my plan is to go from the philosophy. I try to motivate what, yeah.
Do you have a reference about these localities?
No, not really, because it's not discussed in a, no, I don't have. Yeah, it's unfortunately the literature is not very good in many ways. That is, either you have to be an expert to understand. You can look for 542, for example, you can look at the paper of Pickrell. Which is titled Siegel axiom. And maybe there you find some reference, but these are really maybe not, okay. I think it's an interesting paper. It proves somehow that theories like, so he's looking at theories like pi phi 2. We will see something about this. Next thing I want to look at 542. But somehow looking at this theory and try to prove this Markovianity property. Okay, so you can look at the paper. It's not, somehow would require a full course just to talk about this, okay? But, so for the moment, we want just to develop somehow the basic stuff. So I want you to have a feeling what is 542, for example. So the first building block are these local functionals, which we will use as potential in this perturbation formula, okay, in this formula. And then we develop a new way to look at this. So this was the limit. Let's assume you can prove the limit exists, but the basic fact is then in 2 dimensions you can construct a family of random fields which are not polynomial anymore, because you see they were polynomial before the limit, but after the limit there are, you see you can think, for example, of phi 2 is somehow like phi squared minus infinity, okay, which does not really make sense. So you should not think of them in this way. You should just think of them, I took a limit and I got something, okay? If this infinity scares you, it should not scare you because you are aware of that. That is, if you think about, so an analogy I keep in mind, okay, I'm joking in some sense, but I'm also serious. Think about the CLT to understand what is this infinity, what could mean in a real world. You say in the real world there is no this infinity. What does it mean to subtract infinity to a quantity? Well, you do it every day in the CLT, because in the CLT what you do is that you take sum of independent random variables and you subtract a very large quantity, which is the mean, okay? So in the CLT, essentially, you subtract a very large quantity, and you have to think this is similar recentering, and intuitively is a phenomenon which is happening at a different scale, okay? You have to center to this scale to have a limit, and you have to subtract something at a very different scale because it's a different phenomenon which lives in a different scale. This is the law large number, you have to subtract it to get the central limit theorem. Here is the same, there is a quantity which is living in a very different scale, and you call it infinity, okay? So but again, we are not supposed to look inside those objects. They exist, they are functional of the Gaussian free field, which are local, and we will use them, okay? So, and in two dimensions, so what we proved yesterday is that in two dimension, these objects are random field which belong to some order base of space of order C, and we did it on the torus, so I write it down because now I want to talk about what happens in the full space. Yeah.
Just a question for the Hermite polynomials, it forms a basis, right? So
Yes.
estimating function using that. Is there any analog of that once you move to the limit? Is there any sense in which those limiting
Well, yeah, they belong to, so I didn't want to, I mean, there is this book of Johnson, so somehow they belong to the chaos, to the end chaos of the, so somehow they, yeah, I mean, if we want, somehow you have the L2 space of the Gaussian free field, so you create polynomial with nice function of the Gaussian free field, and then with polynomial of degree n, you create like subspace of the L2 space, and then the L2 space become a disjoint union of subspaces, closed subspaces, which actually are the eigenspaces for certain operator, and then these objects belong to that. Okay, so if you want, yeah, because this is why I can use hypercontractivity. So these belong to Hn. I compute the L2 norms, so certainly they are in the L2 space. Sorry, this is not. These are distributions. So somehow you need to test with a test function, and then this is now a random variable, and this will belong to this chaos. So chaoses. These subspaces are called chaos, and this is the end chaos, are polynomial which are orthogonal to all the polynomial of order less, and which belong to that chaos. And also because of this identification, actually they don't depend in the way you regularize, because you have another way to think about them. So this was maybe important, but I'm not discussing any question of uniqueness. So somehow, also because there is no uniqueness in some sense. Well, in this case it's true, but then as soon as we start to do more complicated things, it's not clear. Well, you have to work a bit hard sometimes to get uniqueness. So let's forget about this question of if the limit is unique, if depend your way you regularize. In this case, you can prove it does not. These objects are really intrinsic functional of the natural local functional of the Gaussian free field. They are not the only one. Maybe tomorrow we will see another one, or Monday, if we depend. No, tomorrow I'm free, so Friday and Saturday. Okay, so these are, yeah, so you have these causes, and maybe I will discuss again hypercontractivity later, so this will be important because, yeah, so somehow okay, now if I introduce this decomposition, essentially this is the space, the closed subspace here, which is generated by all the polynomial of order n, which are orthogonal to the polynomial of order n minus 1, okay? And then, okay, maybe later I will need hypercontractivity. So keep in mind these spaces again. Right now I want to, I had in program to look at a different problem. The first thing we could try to do, okay, there are two directions where I want to tell you something about. The first direction is what happened in dimension 3, because this will occupy us next week. So I want to prepare some material. So I want to do the same construction in dimension 3, but in dimension 3 I will start to have problems. The first problem is that if I try, so remember what we did yesterday to prove the regularity. We used these Bezos spaces to represent this norm and another num, and then we converted using hypercontractivity into an L2 estimate. So at the end of the day, or even at the beginning, that is, if you want to understand a random field, a natural thing to do is try to understand its covariance, okay? And then I proved the formula for, I proved the formula with the things regularized, but then you take the limit, and you get something. Here you have the covariance of the Gaussian free field in x minus y to the power n. And then there is a factor which Carlo says is n factorial, but it's n factorial. And yeah, you should believe it, actually, in this case, at least. So n factorial, we don't care about n factorial. What we care about this function in 3 dimensions. Now this function looks like 1 over a small distance. Remember, this was the covariance diverge like 2 minus d. There is d the dimension, and then it was 2 because you had the inverse of the Laplacian. So you get actually d minus 2. So this is 1 in 3 dimensions, and then you get power n. So you have something like this when x minus y is small. This is the situation. And now you see that there is a problem in 3 dimensions, because in 3 dimensions this is 1. And so when n is 3, this function is not integrable on the diagonal. So this cannot be even a random distribution, because if you think that you now smooth out, then you have to integrate this thing with respect to the x and the y. Okay, so essentially what will happen is that the variance, so the variance of phi square f with a test function, you put here a nice test function. Let's say we are, let's stay on the torus, okay? For the moment, we stay on the torus, but I want to go in the full space real soon. So the variance of this, essentially this computation behaves like the integral of fx, fy divided x minus y squared, because it's 1 and square. The x is y, so this is good. This is integrable. It's okay, finite. This is a smooth function, okay? So all you care is what is the singularity and in which space you are. You are in T3, so in T3, on the diagonal is 3-dimensional, so you can integrate 1 over x squared in 3 dimensions, okay? But in 3 dimensions, you cannot integrate the cube because it's a singularity like dx over x, so it's logarithmic. So the variance, so let me write it differently. Now I use the regularization, but essentially, if you try to do this for the cube, in 2 dimensions, it was not really important, okay? This k is not uniform with respect to n, so you cannot fit all these objects in the same space, but for every n, you can find a k, and maybe if I want to be more precise, you can do something like this. Okay, so they lose regularity, but very little as n increase. But here you get a problem, because this object now, the singularity, it's not integrable anymore, so you have to pick up the cutoff, and this behave like log t. Okay, so you see that there is, you cannot hope to have limits, because the strategy we use to have this tightness bound will not work, because even the L2 norm is not bounded. And actually, it's an open problem to, I guess. Somehow it's not written anywhere properly, but somehow the cube should not exist as a random variable. Okay, but this is not written down properly to my knowledge, so you can correct me. I will be glad to update. But for the square, well, the square exists, but somehow if you go in 4 dimensions, you will start to have problem with the square too. Okay, 3 dimensions, this object like this, so the cube does not exist. Okay, so because you see that there is no, well, this is the cube even regularized. Sorry, so this is, you see, you integrate this. If this would be a bona fide random distribution, then it should be, when you integrate with a test function, should be a random variable. And okay, this computation tells you that you don't have hope in L2, so it's not a random variable in L2. so this is all we. So it will not be a random distribution for us. We cannot use the same strategy. So the cube creates problem in 3 dimensions. So I just wanted to say in 3 dimensions the square exists, but the cube does not exist, and the higher power it's worser. So you start to see a phenomenon which is new. Okay, we were hoping that having the idea of random distribution solve all the problem, but it's not true. Okay, random distribution solve some problem, but then you have objects which somehow so the correlation function will exist. Okay, this formula has no problem in any dimension as long as you take 2 different points. So somehow there are something, and for the physicist, the object exists because you can write every correlation function as long as you take different points. But then you cannot interpret them in the language of random distribution. So when you go from real world to physics to mathematics, in mathematics you have to choose a framework where you do your stuff. And you see, Schwarz functions are not the only notion of distribution. It's a choice. Okay, it's a choice we all use, but it's a choice which has even Lebesgue integral is a choice. Okay, there are things you want to do for which the Lebesgue integral is not the right notion of integral. There are other notions of integral. You look in Wikipedia, you find some other. So somehow our setting of random distribution does not fit this object, which should exist in a way. For the physicist, this object should exist, okay? Because correlation function does not have any problem at different points. But somehow in probability, we don't have this notion that you have random variable at different points, because we don't discuss the locality of the random variable in a coherent and very well-defined way. And so this is a feature that in some sense I think is lacking in our formalism. Random variable localized in different sets, and we don't have this problem. Okay, when we integrate, you see what is the problem. Where you integrate with a test function and you try to compute the variance, this will include point arbitrarily near the diagonal. There is no way, because this is the same test function for x and y. You cannot use 2 different test functions. Okay, so this is intrinsic the way we think about this problem. It's not good enough in some sense. Anyway, this was an excursion. Sunday we will do an excursion. This is another excursion. So in 3 dimensions, this will be relevant next week, but certainly this computation is working. This is finite. So certainly we can say something about this. So let's record it here. So the square, it exists, and okay, you have to do exercise for you. You try to repeat the computation we did here to compute the regularity, and you end up with this object which is in -1 minus a small number on T3. Okay, and remember that phi was in -1/2 minus a small number on T3. So this is in 3 dimensions. So the Gaussian free field has regularity -1/2. And the square of the Gaussian free field has somehow -1. Okay, it takes the double, because somehow the correlation function diverges in the square of the other one. Okay. Any questions on this point? So I wanted just to record this regularity will become important next week. Okay, when we try to do something in 3 dimensions. For the rest of the week, I wanted to work in 2 dimensions, but I wanted also to work in the full space. So right now, I want to discuss weighted Bezo spaces. Okay. Because we want to work, okay, I want to work, they become relevant when the space become unbounded. Actually, there is an error in the note. Felipe made me notice it, so, but find the error. But somehow, certainly in the proof we did, yes, in the proof we used that we were on the torus, because at some point you integrate over the x, and this has to be finite. If you do in the full space, at that point the proof does not work. So certainly, and you say, okay, maybe the proof is not good enough, but you know already that this cannot work. Okay, Brownian motion is not Holder function over the full space according to the definition of Holder norm, okay? Because it's growing at infinity. Okay, so it's not a problem of regularity, it's a problem that if you look very far, you win the lottery. So if you live long enough, you will win the lottery. So if you look very far and you have a Gaussian random field, you will see any fluctuation of arbitrary large size because it's a Gaussian, okay? So it can fluctuate, and if it can fluctuate, you will see definitely. So that's the problem. It's not a problem of regularity, it's a problem that we integrate, that either we use LP or we use L infinity, so we try to control this object over the full space. You could define local Bezos spaces where you take your random field, you multiply with a localized function and you're done, but it's easier to do differently. And it's easier to replace things like LP over the full space. Okay, so essentially what we are going to do is to replace LP with weighted spaces, which I write in this way. So in the definition there is only one change to do, is that you have to realize that, okay, how you measure the size of your function is your choice. We use LP norm to measure the size of the delete Pauli blocks. And what we want to do is actually use weighted norms. So let's do this. Essentially, what is this weighted LP? So you introduce a weight. This is a weight. This is this point in the space. And usually the weight we take are of this form, okay? And they are nice function with a very large number here, okay? M is very large. And it's not important what you take. In the notes, what is important that I'm using at some point is that certainly these functions are always different from 0, and you take these polynomial weights. That's good enough for us. In other applications, you could take exponential weights, or you could take compactly supported weights. But then compactly supported weights are a bit tricky to use because you cannot remove the weight. Okay. So let's take this weight. This is kind enough. C infinity, you can differentiate many times you want. The more you differentiate it, the more it decays. Okay, decay more, so everything it's very nice. Okay, and then you define the norm, a weighted norm in LP. There are two ways to do it, and the way which seems reasonable to me. So if you take the norm, it looks like this. So you take the weight. And you multiply with the function, and you take the p power, and you integrate. Okay, another way to do is just you put the weight with the norm. So these are two different ways, and you have to check when you read a paper, you have to check which definition, because half of the paper use one and half of the other. Okay, they have different property, but this is, to me, it's very natural because it just means that you multiply the function with the weight, and then you compute the usual norm. Okay, so I think it's a very natural way to do it. And this, sorry, not L2, LP. And in this way, it works also for P infinity. Okay, so the weighted norm in L infinity is just, you take the function, you multiply with the weight, so you are you are depressing the function. And now the question is, are you depressing the function enough? So let's see what we have to do. Okay, so in L infinity, so now if I look at 0, this is just the norm of F rho in supreme norm. Okay, supreme over okay, something like this. Okay, continuous function. Let's write this. Okay, and in this way, now you can define Bezos spaces with the weight. Okay, so I will have this notation. Okay, so these are Bezos spaces in which you replace the occurrence of the LP norm with the weighted norm. Nothing changes. And they are very nice. And one property they have, for example, is that with this kind of weights, you essentially so measure the size of a function in these Bezos spaces with the weight is the same thing, or it's equivalent. Not really the same, but it's equivalent to measuring the size of the weighted function in the unweighted space. Okay, so if I don't put the weight, usually it's the unweighted space, okay? Otherwise, I always put the weight in the norm. Okay, so this, if you think what is implied in the two is that here you have the blocks, and then you multiply with rho, and then you take some norm, like LP, for example, okay? While here you multiply and then you take the block. Okay, so on this side you will have actually the block of rho f. Okay, so to compare to prove this theorem, like LP in the full space. So to prove this equivalence, what you have to prove is that you can commute the weight and the operator. Okay? It's not true. I mean, this is not equivalent to that. But somehow, if you sum over all I, I mean, the norms are equivalent, okay? But in the task, you have to prove, and that's why you need a weight which is, I don't think this is true if the weight is completely supported, okay? But certainly I can prove, I know how to prove it if the weight is like that. Okay, so this is true. Okay, that's all you need to know because you see, yeah. No, because it could work even with M0, okay? Because this would be, at this level not, then at some point it will matter. So let's try to see where matter. Actually, it's not even clear that this is enough to solve our problem, okay? Because maybe your function grew faster than any power, so you did nothing to improve the situation. So it's just a definition. You can define more larger class. You can single out, axiomatize the notion of weight with the property you need in the proof, and then there is a larger class of weights. But let's say for us, this is a nice class, and you can prove it with elementary tool that somehow the things are okay. So now I want just to check that this will work for us. And again, this makes sure that your theory, whatever you know to do for this space, you do it with the weight multiplied, and then you put the weight in the norm again. Okay, so most of the problem with the weighted spaces are solved by this equivalence because you prove things in the weighted, unweighted case, and then you go back. And sometimes it's convenient to take this point of view, other times it's convenient to take this point of view. Okay, so that's convenient to have this equivalence. Okay, so let's see if we can learn something. Now you want to prove, now you are in, let's do in 2 dimension because I will not study the problem in 3 dimension, but it's the same. In 2 dimension, what you do, so now we take D equal 2 and we take R2, okay? So the full space, this we take lambda to be. And now you want to prove, so I will not do, let's say, you want to control, you want to prove that this power belongs to, B minus, okay, always. Okay, the same thing, let's say, C alpha with a weight rho. Okay, so we will see what we need from these weights. And then, again, okay, so the argument is the same. You start with P. Now I think you are annoyed because I'm repeating the same thing over and over, and I have to go faster. But essentially, okay, Sobolev, again, okay, Sobolev embedding work in the same way because you start here, you go here, you do your Sobolev embedding, and you go back. Okay, so very elementary. So here I have P, I put P, and then here I want to be in B, P, P, with the weight rho, always. And then now is the key point, okay? Now you have, remember, there is the sum over I, there is the integral, and then you have the weight. So now you have the LP norm with the weight. So you have the weight at the power P, okay? Because this is my convention, the weight is raised at the power, okay? So it's inside the norm, and then there were the little Paley blocks of phi n at the point x to the power p, and then it's integrated, and then you take you do Fubini theorem and you put this there. This was so the only thing that changed in the proof that we did yesterday is that you get the weight instead of, and you get the integral over the full space, okay? Otherwise the proof is the same. But now you see that it will work if this weight is integrable, okay? Because now you evaluate this expectation, you use hypercontractivity, assuming you know, but essentially just the idea that I can estimate the p power with the second power, then you do this computation with the second moment, so you estimate this, and this was something which grow arbitrarily little, well, but you have the power p, so this looks like this for the n power, so you can write, something like this, okay? It grows like this if you want, but epsilon is very small. And then you see now, this is homogeneous, this does not depend on,
So the first thing, is there any loss from the smooth?
Sorry, of course, good. I was looking at people watching me say, what is saying? I mean, you have d over p, so you lose d over p, sorry for that, here I lost also, I was too fast, okay? But you understood everything yesterday, so of course it's, here you have d, you have IP alpha minus d over p. Okay, so you have this, and then you have this contribution from the weight. And I don't care, this is like yesterday, so let not me repeat. The point is that this quantity, it's finite if rho to the p is integrable. Okay, this is finite if rho to the p is in L1 of the R2. Okay, this is R2. Okay, but p, I choose p. Okay, p is the number I put it here, so I can take p very large, and so you see, a weight of this form for whatever m I have, it will be okay. So I just need, so to have this, I just need that m times p is bigger than 2. Okay, and then actually, in the way I wrote, so let me write in this way so that it's 2. Okay, but okay, it's not important, just condition that it's integrable. But this just say m should be bigger than 2 over p. I can choose p large enough. I want to choose p large enough because this make my loss very small at that level. Okay, you pay a lot if you want to go from L2 to L infinity, but if you take a p large enough, you don't pay. So then the proof works in the same way. And what you prove, so this gives you that this random field lives in C minus kappa again of rho. Essentially, it lives in this space for any, for any I don't like that in the notation, I don't see things. So let's call this weight rho m in particular. So when I use rho m, I mean this polynomial weight. This could work maybe. And then this will work for any rho epsilon, for any epsilon positive. Okay, so let me write it in this way. Okay, for the moment. Okay, so this means that this random field are in any, you see, you need a weight. Epsilon cannot be 0, because otherwise here there is no way that p can make it integrable. But if you have a small decay, arbitrary small decay, then you can take p large enough and get integrability here. So your random field, you know that your random field has this regularity, this you know, maybe you can put n, because I put n here, but somehow it lives in this space where kappa is arbitrary, for any epsilon positive and kappa positive, okay? So I can write it in this way. So epsilon kappa are meant to be small. And this random field, they grow very little. Actually, if you work a bit harder and instead of measuring things you can measure things differently and then really understand that they grow logarithmically. Okay, so Gaussian random field, they grow at most a square root of logarithm of the distance, actually. Okay, because you see why I could put epsilon. I could put epsilon because here I had p, and P is related to the integrability of my object, okay? So instead of taking power, I could have taken function which grow faster than power, like exponential of x squared, and then I would get logarithmic loss. But we don't need that. It's a bit more technical to get, I just mentioned. So I wanted just to register this, we will need in the future. So you have a price to pay in the full space. If you want to use the regularity of your random field, you have to work with weighted spaces, okay? That's the reason we need to introduce them. Okay, good. So this finished this preliminary part. We discussed regularity of Gaussian free field in 2 dimensions, in 3 dimensions, in the full space, and this will work in 2 dimensions, in 3 dimensions too, okay? Just in 3 dimensions you have just the square. The proof is the same, it will grow with the same speed, so it's arbitrary, polynomially, but arbitrarily small. Okay, so let's go on. Now, the next thing I wanted to present is construction of 542 in the way Nelson did in the 60s. Just to give a comparison, I think I follow the same pattern as Justin. I want to show you what is one technology, because then you can compare with another technology, okay? A little, okay? I'm not saying that it's better, just it's different. There are different ways to approach the problem, okay? So let's look at Nelson construction of 542. This is I will not do everything in detail. I want to give the idea how does it look like a proof on the torus, okay? On the torus, this is essentially from the 60s, it was known. And actually this was the origin of hypercontractivity along Sobolev, okay? Log Sobolev essentially was found. Nelson understood hypercontractivity, so we will use hypercontractivity, and then Gross found out that hypercontractivity is a consequence of log Sobolev, okay? And yeah, but so this was born in this community which was studying these problems, okay? So what is this construction? Remember, okay, what you have, now you know everything, you know this language. What does it mean 542? You try to perturb the Gaussian free field. You are on the torus on dimension 2, and you try to perturb the Gaussian free field with an approximation with a potential. And this is the right normalization constant, and the potential, now we have all the language, is essentially, the right thing to do here is to take a regularization of the 4 power of the Gaussian free field, and you integrate over your domain. Okay, so this is 542. Okay, and you see here I fixed the renormalization. I know what I want to go. I predict this random variable exists in the limit. This I showed you almost surely under this measure. The integral is just the integral of a distribution with the test function 1 in the volume, so this will exist. This is a random variable which has finite variance. And we want to put it here, also in the limit. Okay, I could have taken the limit because now we learned about the limit, but in the proof I need the regularization, so let's keep it there. So we want to understand now, so this would make sense in the limit even, so our problem is to understand the exponential of minus this random variable, okay? And I'm very attentive about the sign because it will not be true if you put plus. Okay, so this is very important. This is bounded from below, so we will see. And so I want to construct this measure, and essentially I want to prove that I want to define nu as the limit, as t goes to infinity of nu t. Okay, and I want to prove that this limit exists on S prime, okay, on what S prime of lambda, but actually it will be absolutely continuous, so it will have the same regularity of the Gaussian free field. So here you can put C minus kappa lambda, okay? because it will be absolutely continuous. So the limit will exist in the space of probability measure on C minus kappa. Okay, so now what I told you, okay? So keep in mind when we are doing the proof, keep in mind that if there would be plus here, it would be false. Okay, so this random variable with the plus will not be uniform integrable in the limit. Okay, so what we are going to prove, and then somehow the proof that the limit exists, it's not much more difficult, is the following. We are going to prove that this family of random variable is uniformly is uniformly bounded, and actually it's uniformly integrable. So here you can put here you can also put a p bigger. So here you have minus. You can put for any lambda. Okay, so let's put a lambda for any lambda positive. This is true. Okay, so let's say in this way. Okay, so it means also not only that, you see, this is a density, will be uniformly integrable, and the limit will exist because this random variable I told you has a limit, so somehow you just need a uniform bound to essentially create a proof of convergence. And actually the limiting measure, so this will exist, so the limiting measure, it's absolutely continuous. Okay, there is a constant, but somehow the limiting measure has a density with respect to the Gaussian free field because essentially we prove that the density is uniformly integrable. Okay? And V infinity is just, V infinity is just the integral of the 4 power of the Gaussian free field. Okay, so we know that this exists, you integrate, you create this random variable, and we do this. Actually, again, I could have just written down this and proven that this measure makes sense because this quantity, it's integrable, okay? But I can do this uniform limit too. Questions? This is what we want to do. So Nelson, how Nelson do this? So the first thing you have to remark is that it will be false if there is a plus here. So this will be not uniformly bounded with a plus. Okay, so false with plus. So if there is plus, this is false. Okay, so any technique you use should be able to distinguish these two things. Okay. So what is the difference between the plus and the minus? Is that the potential has a preference. The potential is created with that's why I wanted to have the regularization. So now you look at the regularization. This is a 4th order polynomial of a Gaussian random variable. So it's bounded from below. It's not uniformly bounded from below because we are going to write it. So let's write it. So if I write this, this is the 4th power. Now we have to remember what is exactly this, but essentially, certainly, it's monic, so we start with this, and then you have to subtract numbers. I don't remember. Remember the 6, thank you, phi t squared, but now it's not normalized, so here you have to put the covariance, and then there is plus 3 covariance squared. This is not very important, okay? This constant is not very important because the potential is defined up to a constant, so you don't care about the constant. What you care is that if now you look at this object, it's a 4th order polynomial, so it's bounded from below, but the bound from below you compute it by finding the minimum of this polynomial. It's proportional to ct squared because this will contribute, okay? So this is certainly bigger or equal to minus, up to a constant to minus ct squared 0. Okay, so this goes like minus log squared t. Okay, so the bound degenerates very fast. Okay, not fast, depending on your taste. So this random variable is integrable because it has an upper bound, okay? But is not uniformly integrable with this upper bound because the bound become worse and worse, okay? But certainly, if you now change the sign, you don't have, no, you have a lower bound for this quantity, but you don't have an upper bound because you have the 4 power and it's a Gaussian, so it could be very large. So this is what distinguishes the plus and minus, but it's not enough to go to the limit. Okay. So we have to do so. So you say why you, yeah, okay, we have to do something about it. And the strategy of Nelson is as follows. Yeah, so the strategy, you have to use this, but this is not enough. Okay, this will give you a bound which is growing with t, because it will be like exponential of plus logarithm square of t, okay, something like that. So you have to repair that. So let me look at my notes. The second, I need, so you need this information. This is the first information you want to use. The second one, this is the first information. The second one, information, it's you try to, somehow t is going to infinity, so you will lose this bound. So you have to stop t, but then you pay a price, which is the difference of where you stopped up to t. So somehow you need to compare, sorry, I just needed, yeah, because I'm looking at the wrong page. That's why I don't find what I was looking for. So I want to have a better lower bound, okay? So what I do, I need to use hypercontractivity. So hypercontractivity again, and hypercontractivity works as follow, okay? If P is a polynomial of order n of my Gaussian, okay? Then I need to be precise what does it mean hypercontractivity. So hypercontractivity means that if now I look, this is now, I have to be careful with the constant, that's why. So there is a precise constant in this inequality. So this is the real equality that I was using also yesterday, but I didn't care about the constant. Sorry, of order, yeah, of order n, then you have n to the power p. So p is the power you raise, and then you can compare with the L2 norm, and then you have power p over 2. Okay, so this is the non-interesting part because we already learned about it. The p power is comparable to the L2 power, but the constant is universal. For all the Gaussian, it's the same constant, and it does not depend on the dimension of the Gaussian, okay? It depends only on the power you want and on the polynomial or the order of the polynomial. And I need this constant, okay? And then if you put together these two, for example, you can look at the notes. You can look at the notes, but somehow, let me go a bit faster. You can ask questions if you think, but essentially Nelson observed that and then invented hypercontractivity. And then, so he computed this you can do a compute. Somehow, if you are strong enough, you take an integer, you do the combinatorics, and you find out what is exactly. You can do even for non-commutative Gaussian, so this is very robust for Gaussians. And then what he did, so he said, well, I want to lower bound the potential. I want to send t to infinity and get a good lower bound of the potential. Then I try to compare with another potential with a different value of t. So let me try, so this is less than, so I want somehow, I need to prove that this is integrable. I need a control on the tail of, on the positive tail of this thing. So I want to study the probability that this is smaller than some level, okay, that is very negative. So then this implies that, sorry, let me copy, otherwise I get, I compare Vt with an intermediate point, let's call it k. So I sum and subtract k, so here I have minus L, and I have minus Vk, okay? But minus Vk, I can use this lower bound for minus vk. So I get something like plus c log square k. Okay, this is essentially, this is the bound for minus vk. Okay, so I add and subtract vk, I put it on the other quantity, and then I do an upper bound on that. So this say that this quantity is smaller. So this probability well imply that. Okay. And then okay, if you do like this and you use Markov inequality, essentially you can have a bound that so essentially you are going to say that Vt is smaller than minus L. This is bounded. Now you use this and you do your computation if I didn't get it wrong. So now you use a Markov inequality to estimate the probability of this event, and you get an expression which looks like this. So you want Vt minus Vk. Let's forget about. So here you use Markov inequality, okay? And this above to estimate the tail of this random variable. So you have p here, and then this is the bound. So this goes to the denominator. There is L minus c log square k to the power p. And this is just going in the denominator. And now you have to make the right choice of now the idea what is? The idea is to make the right choice of kappa. Okay, kappa is a parameter I introduced, is smaller than t. I put it as an intermediate point to compare. So V kappa is bounded from below. By that, I'm using 1. And now I'm using hypercontractivity to estimate this, because this is difference of two fourth-order polynomial of the Gaussian. So I want to use hypercontractivity. So at this level, I estimate con la hypercontractivity, and you get that here you can put Vt minus Vk to the power 2, p over 2, and then you have the denominator as L minus c log, c is a constant, okay? It's just a constant in this lower bound. I was a bit lazy to compute it, to the power p. And then, yeah, you have this, okay? This is, sorry, I forgot, I think in the notes I forgot the constant of the hypercontractivity, but you don't have to forget the constant. It's there is p minus 1, because I take over, it's p minus 1 over p and alpha, okay? It's like, because I'm using a different power. Okay, and when p is large, this is essentially p to the power, n, what is n? N it's 4 for us. Okay, n is 4, because it's a fourth order polynomial. This I'm using that, so here is 2. Okay, and you have 2p. So this is, so here in this computation is so fine that you have to use exactly this constant, okay? I'm just replacing the constant. So here I have 2p because I'm using that n it's 4, because this is a fourth order polynomial. But the difference of two fourth order polynomials. And at this point, you take kappa. So you see, you want kappa essentially, you want kappa so that this become a constant, okay? So essentially, you take kappa such that L minus c log to kappa is essentially 1. This means that kappa has to be, yeah, essentially behaves like exponential of modulo constant square root of L. Okay, should behave like that, okay? Should be large enough. And at this point, you put all together. So this is a computation. Let not me do it. It's done in the notes. I wanted just to... I think this is very nice, and it was the origin of a lot of other discoveries. But somehow what you find, if you now you plug everything together, yeah, and I need to take P also. I can choose P, so let me choose P, because P I was using in Markov inequality. Exponential, and you take somehow this P here, more or less. So you have to choose kappa. I introduce kappa and P as parameter, okay? So I was estimating this probability. I introduced P via Markov inequality, and kappa because I'm doing this interpolation. So I can choose them. You choose large enough, large in this way, and by using the exact constant in the hypercontractivity, and that you realize that the probability that Vt phi is smaller than minus L goes to 0 as some constant up to exponential constant, square root of L. Something like this, okay? Minus 1 proof. Well, it's not very important, okay? It's going like that, okay, morally. So you see that the lower tail of this object is very, very small, okay? It's going to 0 as exponential of minus another exponential of square root. So the lower tail is very, very small. This means that the random variable is exponentially integrable, okay? So this implies that, and these constants are uniform. So this implies that essentially this object, this object exists for every lambda, okay? Okay, so you have this bound. But the upper tail, you don't know anything. It's not as tight, okay? Okay, so this is the key argument now. So once you have this, essentially you can take the limit. This object will converge to the limiting object, and you have the same bound for that. Yes?
How did you upper bound the expectation of Vt minus V kappa squared?
Yeah, sorry. These are, sorry, this was an important, I removed a step, so thank you for the question. I forgot to talk about, so this reduced the problem to an L2 computation. You have to do this L2 computation like the one we did for the regularity. It's an explicit computation. And since Vt converge, somehow this Vt minus V kappa, it's very small when kappa going to infinity, okay, because it's converging, okay? So you have to use this property, sorry. So, use, but this has to be computed, okay? I didn't do in the notes because, but you certainly have to do it. So for T bigger than kappa, but you see, the point is you want to reduce an L2 computation, otherwise the LP computation is messy, you don't see anything. You do L2, from the LP computation, you just need to really care how much you lose. And then this object, since Vt converge, somehow this object will be small when kappa goes to infinity. Okay, so you can say, I don't care about T, will be a uniform estimate in T, but certainly it will go to 0. And I don't think here you need, did I put in the notes? Here you have maybe to be a bit careful, but maybe not, let me think. I forgot to write, sorry, but essentially, somehow this is a nice quantity, so essentially it will go to 0 like 1 order 1 over kappa. Okay, so this play a role. But essentially it's a computation one has to do. Okay, thank you for the question, okay? So this is compute, okay? So this is exercise, exercise for you using. It's a bit annoying, that's why I don't want to do it. But I think if you look in higher lecture notes, there are all the details, okay? Here it was not my point to spend too much time on this. I just wanted to show you particular situation. So the proof is elementary, it's using this very important information and is getting this very nice result, okay? So the weak polynomial still remember that it's coming from the 4 power. It become unbounded, so I mean, it cannot, in the limit it will not be bounded below, okay? But somehow the tail is very small because you remember that before, when he was young, he was positive, okay? But then become very negative, like life. Okay. So it remained mildly optimistic. You see, it's not very, very negative, but so once in a while become negative. Okay, let's stop. So this is the construction of 542. Okay, I didn't prove everything, but once you have this bound, the random variable exists. I claim it exists. So you can this measure exists in a very easy way. Okay, you can give a meaning. You can write down this formula makes sense. Okay, this is a rigorous formula. Here you can write something like this. And now, yeah, there is a constant here. So this formula, it's rigorous, okay? This has a rigorous meaning. The random variable is integrable. So this measure, 542, is a measure which is absolutely continuous with respect to the Gaussian free field. Okay, so 542 is absolutely continuous. So this is 542 and is absolutely continuous with respect to the Gaussian free field. So it is not very different, okay? It's not a very different measure on a finite domain, okay? So this is important that lambda is finite. Okay? You see that if now I want to understand what happened in infinite volume, maybe I still have a problem because this integral will be infinite, okay? The random field is homogeneous in space if I do in a very large volume. This formula is not stable under this limit, okay? So this is now the beginning of the course because I showed you one example. I showed you can construct a theory, but as soon as you want to do in infinite volume or you want to do in 3 dimensions, this is one of the few cases where the measure you want to construct is absolutely continuous and it's easy to construct. And in infinite volume, this will not be true. So absolute continuity will not be true in infinite volume. And in dimension 3, even with finite volume, okay? So in R2, okay, so in R2 or in infinite volume, in 3 dimensions, this is which is the simplest model you can think of. You don't have any chance to get out very easily with standard probabilistic approach to say that is a measure which is absolutely continuous with respect to another measure. By the way, in 3 dimensions, the 4 power, forget about it. So even thinking about the exponent, this will not exist in 3 dimensions, okay? You can write the prelimit object, but you cannot write the limiting object. Okay, so let's forget about this. Now we go on, and the object of this, well, the title is a stochastic analysis perspective. And up to now, there is no stochastic analysis, okay? There is no Brownian motion, there is nothing. This is a probabilistic approach, if you want, okay? You write a measure as a perturbation of another measure. This is not what you do when you study stochastic analysis. When you study stochastic analysis, you solve as this, and you create new random variable by solving equation involving Brownian motion. Okay, you take Brownian motion, you put in a machine, and you create something new. Okay, or even to simulate. Okay, so let's go on. So the approach I choose to explain in the lecture is based on a variational formula. So I want to introduce this variational formula. So all the measure we consider, so again, okay, the measure we consider, they look like this, okay? So they have this general feature. They have there is a reference measure, reference probability, and then there is a potential. And this is called usually partition function. This is a number, but it's called partition function because we usually depend on the temperature. And this is a Gibbs measure. Okay, so this is in general, if you think about a Gibbs measure, means a probability measure which you construct by doing this tilting of a base measure. Okay, now these represent the equilibrium. So in physics, this is known since the times of Gibbs, so end of 1800, and this represents the equilibrium state of a mechanical system. Okay, so it's linked to thermodynamics, and it has a. Now I'm interested to have. So this formula we already used. Okay, this is not stable. It's not a good representation. To at least in this course, we pretend it's not a good representation. We have to find another representation. Then I want to identify this object as the solution of a variational problem, and there is a variational problem associated with this measure. Yeah, let's call it nu v, maybe, just to say this is this particular measure given v. And then I introduce, okay, let's say I have a probability space, omega f. Then I have measure me in the probabilities over omega f. Well, this could be our Gaussian free field, or it will be something else later on. And then I introduce a functional, which depends on v and on a measure nu. So this is a probability on omega. And this functional is just, so the integral of v, so v is a random variable on my space. If v, let's say, is a random variable from omega to r plus, let's say, it's not very important. Well, yeah, okay, r, let's say, because it will not be. And then, so I looked at the average of v, and sorry, I have a problem with the sign, so let me just check. And now you know everything about entropy, so you're not scared about entropy. So this is the relative entropy of this measure with respect to the other. And relative entropy, it's given by the expression Justin wrote, which is this: if nu is absolutely continuous with respect to mu, or if not, you take plus infinity. If not, okay. So it's actually a convex measure in the space of measure, probability measure, and if you don't have absolute continuity, it's in plus infinity. Otherwise, is this explicit expression with the Radon-Nikodym derivative. Okay, infinite, well, discrete state space is exactly what Justin wrote. Okay, but here we are working. It holds more general. So this is a convex function. This is a linear function of the measure. This is lower semi-continuous. This, I don't assume anything with respect to v, but let's say you can assume v is continuous, so this will be continuous for the weak topology. So it is a nice functional, and I want to use it as a variational, to construct a variational problem. I want to find a measure nu which minimizes this function, okay? You know that this divergence measures the distance between nu and mu. So if you want to minimize, you want to minimize this object, okay? This is convex and this is linear, so it will have a minimum, okay? So a good variational problem is the minimization of this object. So argmin, and the space of probability measure is compact for the weak topology in this case. So argmin of this object is exactly this measure. Okay, so this measure is identified as the minimum of this object. Let's say you take V bounded potential, just to simplify our life, but it's too much. Okay, so we identify the Gibbs measure as the minimizer, and this is a meaning in physics. There is the entropy, there is the energy, and the equilibrium system at fixed temperature try to minimize the sum of the two. So this is the free energy of the system. Okay, this is a fixed, if you have fixed temperature. Yeah. So entropy more or less measure how many states you have available. So you want to have a lot of states available, but you pay energy for that, and then you need equilibrium for that. And the minimizer, okay, exercise for you. I mean, especially, of course, it has to be absolutely continuous, otherwise this is infinite. And if it's absolutely continuous, you do a variational computation, and you obtain exactly this formula, okay? And Z appears as a Lagrange multiplier because you have to guarantee that it's a probability measure. But it's a computation. I don't care at the moment. Just for me, it's important that I had another way to talk about that measure. The other way is an optimization problem. Okay, now I have an optimization problem which identify new. Okay, so I want to study the infimum over all the measure of the integral plus the relative entropy. Okay, this problem, I don't know what to do with it. So we need to, you can write it down and then you stop because you don't know how to compare these two quantities. Okay, you need to balance the two. Okay, what is trying to do the Gibbs measure is to balance the entropy and the energy. Okay, you want the measure nu to weight the region of V where V is very small. Okay, because you want the minimum. That's V large you don't like. Okay, is suppressed. So you want nu to go in the region of V which is very small. But if this does not agree with mu, you pay a price. Okay, so you need to compare. You need to balance these two quantities. So you have to bring them in the same language so that they can talk each other. In the discrete state space, you can do in some way. In infinite dimension, is a bit more complicated. And what we found out, it works very well for us, is that you need to have a Brownian motion. Okay, Brownian motion saves your life. So if now, okay, this formula holds in general. This works in many cases. But now I need to specify that mu is let's say mu is the Wiener measure. Okay. So it's not clear why I want to do that, but let's assume that now my reference measure is the Wiener measure, and that the space, let's say for fixed things, let's say I'm in on the Wiener space. Okay, so I'm in the space of continuous trajectory, let's say from 0, 1. To vector space, it could be infinite dimensional, it's not very important. And nu is the law of the Brownian motion. Okay, so this is the law of Brownian motion on 0, 1, on RD. Okay, that's it. Okay, so you are in this context. Now you try to understand this problem in a specific context. This Brownian motion will not be exactly the Gaussian free field. I need to have a Brownian motion, okay? I cannot have Gaussian free field. Why I want a Brownian motion? Because there is this beautiful property that if nu, so now nu is a measure, nu is a probability on this space, or another measure on trajectory, on a path space. Sorry, I lost track of time. It's finished? No, how much time do you have? 17 minutes. Okay, at 4, we finish at 4. By the way, there are talks at the coffee break, so don't go away. I think on the program is not clear, but there are 2 talks later. So don't go away, it's not holiday yet. Okay, we have plenty of time to do a lot of interesting stuff. I think this is beautiful, okay? In a general space, the entropy, all you know about the entropy is this, but on a Brownian probability space, you see Brownian motion has this feature that randomness appear gradually, okay? Because along the filtration, you add the Gaussian, very small Gaussian every time, and there is no space to do a lot of things. And then the filtration create a simplification in this formula. And there is this formula that if nu is absolute, so you don't have chance, okay? You don't want to pay plus infinity. Nobody want to pay plus infinity. So you have to be absolutely continuous. So let's look. What does it mean to be absolutely continuous with respect to the Wiener measure? Essentially, it means the following, that, well, if the entropy is finite, you have a formula like this for the entropy. You have a new formula. It's 1/2 of the expectation of let's say I do 0, 1. Okay, we'll do infinity. It's not important, the interval. Okay, you have a previsible process, which is almost surely in L1. Okay, so U is let's say 0, 1 omega cross omega in RD, previsible with respect to the filtration of your Brownian motion. Predictable. Yeah. And then you measure its L2 norm in average, and if it's finite, you get this formula. So what is the link between nu and nu is that essentially under the measure, under the measure, so if this entropy is finite, there is this drift, and this measure is a Girsanov shift of mu. Okay? So you have you have a very precise structure for the absolutely continuous perturbation of the Wiener measure. Okay, this does not exist in any So a nu is the exponential. Well, d nu over mu is the exponential of the integral of us dbs minus 1. Okay, usual formula. Okay. This you already know more or less. Okay, if you know that if you have measure which is absolutely continuous with respect to Brownian motion, then you can create a martingale from the density, and then this is positive martingale. You have exponential. You can, and then you need the martingale representation theorem to identify the local martingale, but that's all. But somehow there is a theorem that if the entropy is finite, then the drift has to have a L2 norm or finite. Okay, and this is called so U is called Vollmer drift. Okay. Okay, is Vollmer which studied this situation. So for this you need Brownian motion. That's why we introduce Brownian motion. Then let's say under nu x, so b minus the integral of u is another Brownian motion. Okay. Okay, so this is the Girsanov theorem. Okay, if you remove the drift, and this will mean just the primitive of u. Okay, u is in L2, so you can integrate it. It will be absolutely continuous curve, and then you under the measure nu, this process b tilde is a new Brownian motion. Okay, is a Brownian motion. Okay, this is this formula. So this formula. So you see why I wanted to introduce. If I have a Brownian motion, if I'm working on the space of the Brownian motion, this is work only if the only randomness is coming from the Brownian motion. Okay, otherwise there could be part of the entropy which has nothing to do with the Brownian motion. But somehow, if you are in a Wiener space and your measure it's on that space, then you have this structure, then you have a formula for the entropy, and now you see that you improve the situation. You improve the situation because now in this setting you can do the infimum over all the measure, but then you have u, so this measure it's really you can do the infimum over the u, and then now I call the measure nu u, okay, because if it's somehow in this variational problem only the measure which come from this given u, so I call this the relation, I call it nu u. So here I can just optimize over the u. Here I integrate with respect nu u. And here I pay the price. I pay the price of, the expectation under, the expectation of the integral of us square. Yes. Okay. Yeah, and you see that under, okay, now, I mean, in this formula, you can try to, this formula is still not very good, okay? But give us the idea. So it's not very good because here you still have mu. So this is the average under mu, because, sorry, yeah, I think this is mu. Sorry, I forgot to write. But I think this, now you have to measure, you have to be careful, but I think this is mu. So it's not very easy to use because here you have to take the average over nu, and here you have to take the average over mu, so this is not comparable yet. But if you think about this, okay, this will be like the average. So so what happens under under nu u is that v will be a priori is a functional of the Brownian motion, but b under nu is not a Brownian motion, but you can write it as b tilde plus I of u. Okay, but the problem is that I of u is adapted to b. Okay, so there is this slight difference. Okay, this is a real, so you almost manage to write everything under the same expectation. This is what you want to do. But this formula is very unpractical because this process is adapted to something you don't know very well, because you changed measure and now you don't know anymore the law of B under, well, the law of B under the new measure is the new measure, but somehow what you know is this is a Brownian motion under this new measure, okay? So you would like to have, somehow you would like to put them ideally in the same, so let me write in this way. You would like to have a formula which looks like this, okay? This is not possible in this context, so this is wrong in some sense. So I would like to have a formula like this is not working, but essentially, is it true? So, yeah, so this is the attempt, okay? The idea is that you go on this space where you have this nice representation, but then you have to work a bit harder. And by working harder, you convert your problem into this new formula, okay? And so this would be very easy to prove, but it's not quite right. But if you do a more complicated proof, then you can prove the following. This is called the we call the Boué-Dupuy formula. And essentially, yeah, you have to recall that somehow the partition function is, yeah, okay, let me write the formula, then I discuss somehow. You have a formula like this. I put them, yeah, let me put the minus because I like to have this minus around. So if you have, now I write expectation because I don't, so somehow this is expectation under mu. This is Brownian motion, okay? And this is a number with the potential V, and then you can write this as, now the minimizer, this would be like the free energy. So it's the value of the minimizer I wrote before, and then now you can write as infimum over these previsible processes adapted to B. And then you have the formula you wanted to have, okay? You want to have a formula essentially which looks like this. It's V of B plus the integral of U plus 1/2 the entropy, but written in this nice way with the drift, okay? So now you have a formula like this, okay? So this is Boué-Dupuy formula, so U is essentially is adapted to B. Okay, B is the canonical process, if you want. And you have a formula like this, okay? So what here was a difficulty because somehow you could not put these two expressions in the same average. Here you have a single measure and you optimize over all the shift. Okay, so this is an optimal control problem, okay? You want to solve, you have a terminal cost, or you have somehow some cost. This could depend on the full trajectory. You have a running cost because of your drift, so you can push your Brownian motion in such a way to minimize V, but you pay a price, okay? You pay the size, okay? These represent this quantity, okay? This is a general formula, essentially. Okay, let's see, for example, how to use it. Maybe today, yeah, I just have time to show you how to use it. So I will not do the proof because the proof is interesting, but it's not very important to apply this formula. Okay, you don't learn a lot. So as far as I know, I observe by using this formula contains everything you want to know. It's an equality and can be used, for example, to estimate integrability of random variables, okay? Because it's an equality, so if this is infinite, this will be minus infinite, okay? Something. well, you would write different. Sorry, I wrote it in this way because I wanted to have a problem like the problem of the Gibbs measure, and you have minus minus. But if you put plus plus, then you have a supremum, and then you have minus here. So the entropy try to compactify. Okay, let's try to use the formula. Yep.
The general V is a path function. So
Yeah, V could depend on the full trajectory.
Exactly.
We will not use this freedom, but this is a general formula. If V depend only on the final value of B, you have easy way to obtain this formula. This formula can be used to obtain functional inequalities or other things, but let's use for a moment. So let's assume that B. So you see this formula, why I'm interested in this formula. First, to give you another way, well, you see what has to do with the Gibbs measure, okay? But somehow you have to keep in mind that the minimizer of the variational formula was the Gibbs measure. So here, the minimizer of this object will represent the measure I'm interested in, okay? The minimizer of this object, it's really the measure mu reweighted with this weight. Okay, so if you have an optimizer, this is not guaranteed, this is an if. We will have to work a bit around this, but let's say assume you have a minimizer, then you have B, okay? So if U is a minimizer, what will happen is that B plus IU, so the law of B plus IU for a minimizer, okay, let's call it U star, is exactly the measure, the Gibbs measure, okay? And essentially this quantity is, well, Z is this, okay? So the minimizer represents the Gibbs measure you want, okay? So you don't lose track of the original problem, just it become a bit strange, but the advantage is that in this formula, you have these two quantities in the same place, so you can compare them, and this is what we are going to do. This is very important for us. So let's do an example, very easy. I think maybe I don't have much time to do the example. I have 3 minutes, so full of time to do. So the example is, I have to put assumption on V. I do exactly the same example. I cannot do Herbst's argument, but it's the same flavor. So take a functional V, which is Lipschitz, in the sense that when you shift the Brownian motion by some function, you get a linear perturbation. Okay, so I will do an assumption like this. Take any function V of the Brownian motion so that when you shift, okay, I can do an assumption like this. When you shift, this is smaller than, I can do very general thing, but just to understand, let's assume that it's Lipschitz. Okay, so I can compare in this way. Okay, and then you can, and the right way to compare here is that you use the L2 norm of U. Okay, because of course here you have the L2 norm of U. Okay, L2, 0, 1. So this is an assumption on V. Imagine your preferred functional. For example, you can take a stochastic integral will satisfy this hypothesis. Okay, because when you shift the stochastic integral, you will, okay, here you need a constant. So you call L the constant. Okay. Now, if you have a bound like this, and I try to estimate theta, you use theta, no, for the parameter. So theta V of B. Okay, now you use this formula to try to prove exponential integrability of this functional. Now you use this formula, you have to put the plus and the supremum, but essentially this is equal to the supremum over U of, well, the log, you have to take the log because you work always below, and then you take exponential theta B shifted minus the entropy, okay? I changed a bit of signs, but this is the L2 norm of U. Okay, I want to, when you use upper bound, this is the nice way to write that formula, otherwise this is the other way. Okay, just you put the minus in the right directions. And the only thing that change sign is the entropy. So you see now you have to take the supremum, you want to make this large, but this pushes you down, so you are fine, okay? This is, you have hope to, and now you see that you are very happy because this cannot grow more than linearly, and this decreases quadratically, so you will never be able to make it very large. Okay, so you say this is smaller, then the supremum over U of the, well, you take the, so you pay what? Theta VB, okay, at most, maybe absolute value. Yeah, let me do one-sided bounds, okay? I just need one-sided Lipschitz condition to do this argument. And I take theta positive, okay? This is really like just a situation, okay? But he wrote the probability, but then from here to Markov, you use a Markov. So I do an upper bound, so this cannot be larger than this, plus theta L, the norm of U, and then you have 1/2 the norm of U squared. Yeah, give me 2 minutes to finish this, because this is the key point. When you understand this, all the rest of the course is exercise for you. So see what happened, okay? Now, this function, I could have a very, we are trying to estimate the probability law of this object. And this formula is so nice that okay, this is the expectation of the object. It's like Justin said, I don't care, it should exist, but I don't have to estimate it. All I have to do is try to have a good bound for the supremum, and this object is a polynomial of the norm of order 2. So I don't care about any, you don't have to know probability theory. This is bounded above by a number which is, should be theta squared L squared divided by 2. Okay, this is, for any U, okay, this is analytic argument. There is no probability. It's pathwise, every U, you have this bound. So you get your final bound, which is theta for the average of B, plus theta squared L squared divided by 2. And you can check that this is exactly, because this tells you that after centering, the object has Gaussian tails. Okay, so Lipschitz polynomial in infinite dimension, you could have an infinite dimensional Brunner motion, it's the same argument. Then the norm would be more complicated. But no, it's exactly that, okay? So this is the key. Why this formula, it's nice for us, is because it converts a problem in probability theory into a problem in analysis, which you can solve with analysis tool, okay? Here we are solved with the tool that the square grow faster than the linear function. Okay, and you don't even have to look that it's a norm, it's just a number. Here you have the number square, you're done. Okay, of course I tuned my hypothesis so that I can do that, but this is the point. Okay, you control the square, the L2 norm, so if you can bound this object with the L2 norm, you're done. It could, and actually you see that you have freedom. Okay, now that you understood my argument, you say, well, but this is easy. I could take any power here until this power can be beaten by this square, I'm okay. So actually, things which grow worser until alpha is less than 2, you are okay. You can do that. It's not this argument, but it's similar argument. And I guess from this you can get also hypercontractivity, but I still haven't finished the proof. So, okay. Okay, let me stop here for the moment.